Welcome to the Chapter 3, Part 2 video, picking up from where we left off in class. So we're going to look at applying systems of inequalities to a question like this. We have $40 in our pocket and we have room in our garden for 15 tomato plants. We want the most pounds of tomatoes that we can get. So think about how you would do this. Go ahead and put it in Edpuzzle. No wrong answer, just think about how you would do this. So give some serious thought to that. And then by the end, we'll have a mathematical solution to this. What is linear programming? Linear programming is a method for finding the minimum or maximum value of a quantity. So like we were looking for the maximum number of pounds of tomatoes that we can have given a set of constraints, right? We can't have infinite number of tomato plants. So the way that we look at those constraints is a set or a system of inequalities. Okay, so the constraints are a set of inequalities. And what those give us when we look at where all of those inequalities intersect, so the overlap of all the inequalities is called the feasible region. This is the overlap of the inequalities. Okay, and the quantity that we're trying to maximize or minimize, the value that we're trying to find the best solution for, is called the objective function. So in our previous example that we were looking at, the objective function is the pounds of tomatoes. Okay, sometimes this is cost, sometimes this is profit. In our example, it was pounds of tomatoes. So let's look at setting up that problem that we were looking at. We have two variables. We have the Roma tomato plants and the cherry tomato plants. I'll call X Roma plants and Y cherry tomato plants. Okay, then we know that we can spend no more than $40. For each Roma plant, that's $2 each, so that's 2X. For each cherry plant, that is $3 each, so that's 3Y. And it has to be less than or equal to $40. That's as much money as we can spend. So this is the cost function. We also have room for at most 15 tomato plants. So X plus Y, the number of plants that we have, has to be less than or equal to 15. This is the number of plants. We also need to have a positive number of plants. We can't buy a negative number of plants. So that's what this last inequality statement says, is that no negative number of plants. And then we want to graph this. So if we take our first equation and we solve for y, we would have 3y equals negative 2x plus 40. Divide everything by 3. Y equals negative 2/3 x plus 40 over 3, which is about 13 1/3. So 10, 11, 12, 13 1/3. Okay, if we wanted to calculate this so that we have some nice integer values, I don't want to substitute just any value for x. I want to try values of x until I find a nice point. Okay, so I'm going to make a little xy table over here. When x is 1, that would be negative 2/3. So that would be 40 minus 2 over 3. 40 minus 2 is 38 over 3, which doesn't reduce. It doesn't reduce to an integer, I should say. When x is 2, we have 40 minus 4 over 3. That's 36 over 3. 36 over 3 is 12. Okay, so 2 comma 12. 2 comma 12. Now that we have a nice point, we can use that slope. Down 2 over 3, down 2 over 3, down 2 over 3, and keep going until we have our line. So there's our first inequality. Testing a point, if we have 0 plus 0 is less than or equal to 40, that works. So we would shade down here. Now I'm only shading in quadrant 1 because of this last restriction. If our number of tomato plants has to be positive, I can only be in quadrant 1, positive x and positive y. Our next equation, I want to solve for y. I would get that y equals negative x plus 15. So that's starting at 15 with a slope of -1. This will be my line. Testing 0, 0. 0 plus 0 is less than or equal to 15. That works. So again, I'm shading towards 0, 0. But then, like we were doing in class, I only want to take the part that overlaps. And so the part that overlaps is just from the corners to the corners, this region in here, the part that's both red and black. Okay, so just this part inside of both and inside of quadrant 1. Okay, so we've programmed our linear system. We have found our feasible region. The yellow is called the feasible region. Okay, so what do we do with that next? Well, once we have our feasible region, we can use a theorem that says or a principle rather, the vertex principle of linear programming, which says that no matter what, our maximum or minimums have to happen at the vertices, at the corners. Okay, so in our last example, we had kind of this shape. Then our maximum number of tomato plants has to happen at one of those 4 corners. Okay, so let's give this other example a try, and then we'll return to our tomato plants. What point is in the feasible region maximizes P for the objective function? So again, we can sketch out our inequalities and find our feasible region, but because this is multiple choice, I'm going to leave that up to you. I put a graph there if you want to sketch it, but I want to show you how to test these points. So if I'm testing these points, we want to maximize P. So I'm going to do X, Y, P. So for point A, X is 2, Y is 0. P is 2 times 2 plus 0. I'm substituting into P, and that equals 4. For option B, I'm substituting again 0, 0. So then P is 2 times 0 plus 0, which is 0. For option C, X is 3 and Y is 1. So that's 2 times 3 plus 1, which is 7. And for option D, we have 0 and 2.5. So 2 times 0 plus 2.5 equals 2.5. Now we want to maximize. Maximum means the biggest. So which of these is the biggest? 7 is the biggest, so that's going to be C as our answer. Now what you'll find is if you decide to graph these constraints, you will end up with these 4 points as your corners. Okay, so I really want to focus on the tomato plant problem. So we're not going to graph this together, but I encourage you to try it on your own. So let's take a look back at our tomato plants. Okay, so for our tomato plant question, we have our graph here. And now we're going to take our last step, which is to maximize the number of pounds. Okay, so I've created the equation for pounds. From our Roma plant, we get 8 pounds. From our cherry tomato, we get 10 pounds. So for every Roma plant we buy, there's 8x, 8 pounds per that plant. For every cherry plant we buy, we get 10 pounds. So we're going to test these corner points, x, y, pounds, which is 8x plus 10y. And our corners here, we have 0, 0. We have 15, 0. We have 5, 10. And we have 0, 13. Right, so I'm finding the corners and I'm looking at the coordinates of those corners. So let's start with 0, 0. 8 times 0 plus 10 times 0 equals 0. I don't think that's going to be our maximum. Let's try 15, 0. 8 times 15 plus 10 times 0 8 times 15 is 120. Let's try 5, 10. 8 times 5 plus 10 times 10. So 8 times 5 is 40 plus 100 equals 140. And lastly, 0, 13. 8 times 0 plus 10 times 13 equals 130. So which one is our maximum? Which one gives us the most pounds? Is 140. And that was our 0.5 comma 10. So the answer is, I want 5 Roma plants and 10 cherry plants. Okay, so think back to how you did this before we had learned linear programming. That first question that I asked you in this video. Is this the same answer that you got? And how did you figure that out? Linear programming is just the algebraic approach to that process. Okay, maximizing the number of pounds of tomato plants that we could get. Okay, we're going to practice this together in class, but what I would like you to do is, for homework, go ahead and try these 4 problems. You're going to graph them, and then you're going to name the vertices, okay? That last step that we just went through of finding the actual answer is optional. If you are ready for that challenge, go ahead and try it. If you're not really sure what we did in that step, we're going to practice it again together in class, okay? If you have questions, email me. Otherwise, I will see you in class.